Swayam Prabha. Digital India. Educated India.
Welcome everyone on the fourth tutorial session of Geology and Soil Mechanics course. So today we are going to continue our discussion on permeability, and today we are going to discuss some very a higher level problems on permeability, especially on seepage and flow lines. So basically today we are going to discuss about the Casagrande solution and a little bit of mathematics about how to use the parabolic equation to draw the phreatic line. So let us start with the first problem, which says that a dam is given to us, where basically the water at the upstream level is at a height of 32.81 feet. And the water on the downstream level is at 0. So basically now you are not given the phreatic line, and you have to draw the phreatic line through this earth dam. The other dimensions are given as: the top of the dam is given as 13.12 feet, and this height is given as 6.56 feet. The permeability of the earth dam or the soil is given as 7.874 into 10 to the power minus 5 inch per second. So now we are going to draw the phreatic line first, and we will take help a little bit of mathematics here from the parabola. So the first thing is that the height h of water on upstream side is equal to 32.81 feet, that is this height. And the projected length of slope on the water surface will be equivalent to the slope of this line multiplied by the height. So basically this is nothing but this slope is given as 1:1, that means this is 45 degree. So this will be equivalent to 32.81 feet as well. Now this length is 32.81 feet, and this length as well is 32.81 feet. So as we have discussed in the lecture, that the parabola will start from a point which is basically at a distance of 0.3 delta, where delta is 32.81 feet. So the required starting point will be equivalent to 0.3 into 32.81, which is equivalent to 9.84 feet. So now our dam upstream level is known to us, as well as you know from where basically the parabola is going to start. So this distance is known to us. This distance is given as 9.84 feet. So this is the starting point of our parabola. So this is where the parabola will start. Now we all know that if is focus of parabola, and the point F lies exactly here. So, this is the focus of the phreatic line, because the phreatic line itself is a parabola. So, taking a little bit of help from the mathematics, directrix to focus distance is given by y naught. Now, this will be equivalent to this length is d. So, this is equivalent to 68.9 feet. Now, I already know that this length is 13.12 feet. So, 68.9 feet. So, this will be equivalent to d square plus h square minus d. Now, d is given as 68.9 feet. So, this distance will be equivalent to 68.9 square plus, as we have found out that the height h or the height of the water in the upstream level is 32.81. So, that is 32.81 square minus 68.9 is equivalent to 7.413 feet. Remember that these slopes are in 1:1, that means they are in 45 degree. So, now we have known the distance of directrix to the focus. Now, we will find out the distance of vertex of the parabola. From focus. Now, that will be equivalent to y 0 by 2. So, that will be equivalent to 7.413 by 2, 3.706 feet. Now, all these relations come from basic mathematics. So, basically I am not going to discuss all these relations here, you have to remember these relations. So, now you have to find out the xy coordinates of the basic parabola. So, the x coordinate of a parabola, because we know that the equation of a parabola is generally given as y minus a whole square is equal to 4a into x minus b. So, from this basic relation we can get that y square minus a square by 2 a, sorry, this is a dash. So, y square minus a square by 2a. So, this will equivalent to y square minus, now a square here is the vertex of the parabola. So, sorry, the distance from the focus. So, basically it will be 7.413 square by 2 into 7.413. So, this is equivalent to y square minus 55 by 14.83. So, we get y is equal to root over of 14.83 x plus 55. Now, the x at different points are known, because this is the x grid, this is the y grid. So, the x at different points are known to you. If you start from 0 point, then basically you can take different point, because it is 68.9 feet. So, you can take points like, let us say 0, then 15, then 30, then 45, and this is then 68.9. So, taking all these relations, you get the values of y as 7.416, then 16.65, then 22.36, then 26.88 and 32.81 respectively. So, this is how you draw the phreatic line. So, now if you take the entire embankment, then this line will be dotted, but it will start from here and in here, and then from here again this line will be dotted. So, this is your phreatic line, that is the equation of y square is equal to 2y0 x plus y0 square or 2ax plus a square. So, this is how you can find out the phreatic line. Now, let me repeat this entire part. The first thing that you are going to do is find out the focus of the parabola. You know what is the focus of the parabola. The focus of the parabola is at the base of the dam. So, first you are going to find out the distance of the directrix from the focus, and that you are going to find out with the simple relation d square plus h square minus d. Now, d is basically the distance of the d is basically this distance, where basically you find out the point 3 delta for basically the phreatic lines, or basically you can say the point in the water where basically the phreatic line starts. So from there to the end point of the embankment is basically the distance d. Now it may be either given to you or you have to find out from the mathematical relations. So d square plus h square, h is the height of the water on the upstream side, minus d. From there you find out the relation of y naught. Now the distance of the vertex from the parabola is exactly half of the distance of the direct to the focus, which is a property of the parabola. So basically from there y naught by 2, and there from there you find out the vertex distance of the vertex from the focus. Utilize that relation in the equation of x, and basically you will find out that what is the relation between x and y. That is what we want to find out, because that is how you are going to find out the phreatic line. Now let us consider, this is just a basic problem. Now let us consider this problem in a more advanced level. So here basically the problem is now given to you as an earth dam is anisotropic. So the figure for this earth dam is actually given, and it is given as this slope is given as 1:2.5, and this slope is given as 1:2.5. This distance is given as 15 meter. The height of the earth dam is given as 20 meter. The height of the water on the upstream side is given to be as 18 meter, and there is a blanket drain that is provided, then that is a distance of 15.5 meter from where the blanket drain is provided to the end of the earth dam. Now you are asked, just said that the hydraulic conductivity of this earth dam in horizontal and vertical directions are respectively 4.5 into 10 to the power minus 8 meter per second and 1.6 into 10 to the power minus 8 meter per second. Now you are asked to find out the quantity of seepage through the dam. Now we all know that basically when there are two different coefficients of horizontal and vertical permeability, then what you have to do in case of an earth dam, or basically when you have to draw a seepage or a flow net, is that you have to consider a transform section. So this is what we are going to consider, the transform section. Now how do you consider the transform section? You multiply the horizontal distance by a certain factor and keep the vertical distances same. So what is the, so how do you solve this? You multiply the horizontal distance by root over of kz by kx, this factor, and keep the vertical dimensions unaltered. So if that is the case, then 1.6 into 10 to the power minus 8 divided by 4.5 into 10 to the power minus 8 is equal to 0.6. So every horizontal dimension is going to be multiplied by 0.6 while the vertical dimensions are kept same. Now let us see that when you multiply with the 0.6, then how does your dam look like? So now this is the dam, this is our earth dam. This is the z direction. This dimension is obviously, the vertical dimension is unaltered, so this is obviously 18 meter again. The height is 20 meter again, and the horizontal length, I mean this length whatever it is has been multiplied by 0.6 into x, whatever the dimension may be. This is what is the altered dimension. Now let us see that how to solve further. So the equivalent coefficient of permeability first you have to find out. So the equivalent coefficient of permeability is kz into kx. So this comes out to be 4.5 into 10 into 1.6 into 10 to the power minus 8. So, this comes out to be 2.7 into 10 to the power minus 8 meter per second. Now, again you have to take help of whatever we have done here. So, basically now you have to find out the phreatic line. So, for that you have to take help of the parabola. So, how you are going to take help of the parabola? Now, the focus of the parabola is at the point A. So, basically the blanket drain is here. Now, what is the advantage of providing a blanket drain? That has already been discussed in lecture, but still I am telling it that basically the blanket drain will reduce the flow net here. That means, basically if a flow net actually goes here at this point, it will bring down the lines here. So, now instead of the directrix, instead of the focus of the parabola being at this point, now we have the focus of the parabola at this point. This is now not the point, because all the phreatic lines as well as all the, because the phreatic line as well as all the flow lines and all the flow lines will come at this point, will all merge at this point. So, basically now this is the focus of the parabola. So, at this point A, again you have to find out this 0.3 into sigma, 0.3 into delta, sorry. So, 0.3 into delta is given by 0.3 into 27. Now, this is obvious why you got this 27, because this is 0.3 into 0.6, because this is the horizontal dimension that is multiplied. Now, as we have seen that this ratio was in 1:2.5. Now, since this is 1:2.5, so this has been multiplied by 2.5 into 18. So, this comes out to be 8.10 meter. So, then you know now that this distance is actually equivalent to 8.10 meter, because and this is the point from where the parabola is going to start again. So, once we know that this point is equivalent to 8.10 meter, now what we are going to do is that we are going to find out the coordinates of point G. Now, what is the point G? G is basically this point. So, how do you find out the coordinates of the point G? Now, you have to first consider that what is the 0 0 point. Once you find out what is the 0 0 point, then from there you find out the coordinate of the point Z. Now, obviously the Z along the Z direction, it is 18 meter. So, GZ is 18 meter, while GX is equivalent to 40.80 meter. Now, 40.80 meter, if you consider along this length, because this is where the vertex of the parabola, this is where the focus of the parabola is. So, once you consider this is the focus of the parabola, from here if you consider this length, then it comes out to be 40.80 meter. So, if this is correct, then we will take help of this equation, the basic equation of parabola, x is equal to y square minus a square by 2a. So, x is equal to, here instead of y square we will let z0 square minus 4a square by 4a naught, the same as this equation, y square by 2a, you can write that as well, z square minus a square by 2a naught. Okay. And from here we will get the relation, because here basically 4a square is given of the fact, because you know that the vertex or distance of the vertex from the parabola of the focus is actually y naught by 2. So, that is why this has been this a square, this 4a square and 4a naught has been added, because we all know that here basically a is equal to 2 times of y naught. So, this comes out to be z square minus 4 y naught square by 2 into 2 y naught, which basically is z square minus 4 y naught square by 4 y naught. If you consider a is just 2 y naught, where a by 2 is equal to y naught, where y naught is the distance of the vertex from the parabola, this number. So, now if you put the values, then you will see that x for a particular point is actually known to you. Now, which point for x for which point is actually known to you? X for this point from where the parabola has started is known to you. That is why you have found it out for the g point. That is why you have found it out the z and x coordinates of this g point. So, now you just put those values. So, for x is 40.80 meter for this point, z square is 18 meter. So, 18 square minus 4 y naught square by 4 y naught. So, solve this equation, then it comes out to be 4 y naught square plus 163.2 y naught minus 324 equal to 0. So, we get y naught is equal to 1.9 meter. Now, if on if basically we consider the sign, if we keep the symbols same, then basically this is not y naught, but this is actually y naught by, because this is actually not y naught, but this is actually y naught by 2, 1.9 meter. So, distance of vertex from focus is 1.9 meter. Distance of vertex from focus we have established to be 1.9 meter. So, if that is the case, then we will just substitute this y naught value in the equation, that is 1.9 meter. We will just substitute this in the equation, on the original equation, x is equal to z square minus whatever the original equation was, z square minus a square by 2 a naught, square minus a square by 2 a naught. So, this comes out to be z square minus 1.9 a square by 2 into 4 into 1.9 square. So, this comes out to be z square minus 14.4 by 7.6. Now, this again let me tell here that basically this y naught, that whatever you have found out, this y naught is nothing, because we have considered that y naught is actually a by 2. So, basically this is the distance of the vertex from the focus. That means, it is equivalent to distance of the vertex from the focus, distance of the vertex of the parabola from the focus. So, in order to get the actual y naught, you have to multiply it by 2. So, that is what we have done here, that y naught into 2, 1.9 into 2. So, if you now put that is equivalent to a or whatever you say. So, whenever you put the values, then this is what is the equation. Now, let us follow the similar process, that you know the x for a series of numbers, which basically starts from, let us say 0, then 5, then 10, then 20, then 30, and the z for all those values will be 3.8, then 7.24, then 9.51, 12.9, 15.57. So, these are the values that we will get. Now, let me repeat this before I again, let me repeat this procedure before I again go to. Now, what we did was that initially first we transformed the entire section. Then what we did was that, just like the Casagrande method, we just multiplied it with 0.3 delta. Now, I have multiplied with 0.3 into 27, because 0.3 is the 0.3 factor, 0.6 in order to transform that 27 meter, in order to transform that 18 meter. Okay, in order to transform the 18 meter on the horizontal length, we have multiplied with 0.6, and then basically multiplied with 2.5, because the slope is in the ratio of 1:2.5. So, we got 8.10 meter. Now, 8.10 meter is basically where the parabola starts in water. So, that point, if we call that point by G, then G has the, we found out the coordinates of the point G. So, G has two coordinates along x and z direction. So, for z direction it is obvious that is 18 meter, because the height of the water on the upstream side is 18 meter, while G for x direction is basically 40.80 meter, that you can easily find out from all the given lengths, 15, 40, from all the given lengths, because we know that this length is 15 meter, and once we know that this length is 15 meter, then we know that how much is this length, because this length is again 18 meter. Similarly, this length is also 18 meter. So, multiplied by 2.5 and you will get all the required lengths. So, from there we actually found out that Gx is equal to 40.80 meter. Once we found out Gx is equal to 40.5 meter, since that point already lies on the parabola, so basically what we do is that we substituted that value of x and z in the original parabola equation. Now, you all know that in the equation of the parabola, that the equation of the parabola actually consists of z square minus a square by 2 a naught. Now, this a is nothing but the distance of the directrix from the parabola. That is what we have said previously, that a is nothing but the distance, distance of the directrix from to the focus. Okay, distance of the directrix to the focus. So, since this is the distance of the directrix to the focus, we also know that the distance from the vertex to the focus is basically half the distance of the directrix to the focus. So, that means y is equal to a by 2, y naught is equal to a by 2. That is what I have said here. So, just substitute the value of a, just substitute the value of a, we get that z square minus 4 y naught square by 4 y naught, that is the equation that we want. So, now just you substitute the value of x and z, so you will get in terms of y naught. You can also substitute the value of just x and z to get a as well, means a, you can also substitute the value of x and z to get a as well. So, we get the substitute the value of x and z to get the value of a as well, like let us say this is 18, this is 40.80, and this is 18 square minus a naught square by 2a. Okay. That also you can do. Any one of the processes is applicable. So, then you can find out the a, which basically will be equal to 3.8 meter. Once we found out the value of a, then you can find out from a easily the y naught, and then you can substitute the value back to get the values of what corresponding values of x, what are the value of z. So, now for the entire dam, you know what is your phreatic line. So, here is the phreatic line, and this is the equation of x is equal to z square minus 14.9 by 7.6. This is what is the equation of the phreatic line, where this is x, this is z, and this is where the blanket drain starts. So, similarly, all the points, that means all the flow lines will be like this, and all the equipotential lines will be like this. Perpendicular to the flow lines. We also know that the height of the water on the upstream side, that is this height, is 18 meter, because all the vertical dimensions are unchanged. So, once this point this has been done, then once this has been done, now you can easily find out that what are the number of drops. So, in this case the number of flow lines are basically 3.8, 1, 2, 3, and this is 0.8, let us say, and the number of drops basically is considered to be 18. So, then Q is equal to K E into H into NF by ND. Now, we all know that the height of the water is 18, because on downstream side there is a blanket drain. So, it is 0 almost. K E, or the equivalent coefficient of permeability, that we have also found out that basically is equivalent to 2.7 10 to the power minus 8. 2.7 into 10 to the power minus 8 into number of flow lines, that is 3.8, number of drops 18, multiply it. So, 10 to the power minus 7 meter cube per second. So, that is how you basically found out using the flow net what is the value of the seepage loss. Now, for this, let me tell you that for this a little knowledge of mathematics is required, because the only fact that you know the equation of the parabola, and this has already been discussed in the slides. And one thing that is very important when basically it is an anisotropic dam, then you have to always remember that you have to multiply the horizontal distance by a factor. Here the factor is 0.6, it is basically the ratio of kz by kx, that is the permeability in the vertical direction by the permeability in horizontal direction, square root, and all the vertical dimensions are to be unchanged, kept unchanged. Okay. And also the equivalent coefficient of permeability has to be found out. So, from there only we found out that what is the value of Q. Now, another question that is asked here is you have to find out the effective stress at a certain point. Now, that point where basically the effective stress has to be found out is at this point P, which basically has a coordinate of 45 meter of x and 5.5 meter of z. So, how do you find out that what is the pore pressure at that point? That is pretty easy, because first find out that if you draw the flow net, first find out that what is the drop at that point. Okay, that means how many drops are basically the point is experiencing. So, here we will see that basically the total drops, the total number of drops or ND is basically is 18. So, 18 drops means in order to get from 18 meter, since the head on the upstream is 18 meter. So, from in order to get from 18 meter to 0 meter, 18 drops are required. So, what is the drop? So, what is the then head loss per drop? That is obviously 18 by meter by 18, that is equal to 1. So, what is the number of drops when basically you cross at the point P? Now, from the diagram, here, if you consider this is the point P, then basically let us say that 2.4 drops are observed when basically it is at the point P. So, if the number of drops is 2.4 at point P, then total head drop at P is obviously equal to 1 into 2.4, that means 2.4 meter. This one is equivalent to head loss per drop. So, total head is 18 meter. Head at P will be equivalent to total head minus head drop at P. So, that is 18 minus 2.4 meter is equivalent to 15.6 meter. So, the pressure head at point P has been found out. Now, let us consider the datum head, because we already said that when basically you have to find out the pore water pressure at a certain point and under any conditions, especially in soil, then basically you have to consider the piezometric head. The piezometric head means it is the sum of the datum head and the pressure head, because the velocity head is 0 as the flow of water through soil is very less. It is like in 10 to the power minus 8 meter per second, 10 to the power minus 9. So, basically the velocity head will be very less. So, pressure head plus datum head. Now, the pressure head at point P is 15.6 meter, and what is the datum head? We have already said that this point P is at a distance of 5.5 meter from the base. So, if we consider the total height, that means the total height of the dam is minus 5.5 meter. If you consider the total head of the dam, means this height as h, then basically the elevation head starts from here, that means this is 0, this point is 0, because we considered this point to be 0. So, z starts at this point, this is where the blanket drain starts. So, along z, since it is going upwards, so basically the pressure head is dropping, the datum head is dropping. So, since the datum is dropping, so that is why we have subtracted it, that means it is minus 5.5 meter. If it goes downwards, that means the datum head is actually being added. So, 15.6 meter, because you know that the pressure head at the lowermost point is highest, or the datum head at the lowermost point is highest, and as you go up, negative heads come. So, 15.6 minus 5.5 meter, which comes out to be added to be 10.1 meter. So, the pressure at this point will be equal to gamma W into the total head, which is nothing but the piezometric head, so this is 10 into 10.1 kilonewton per meter square, or kPa, equivalent to 100 kPa. So, that is how you find out the pressure head at this point. Now, again let me tell you that this is quite easy, because once you draw the flow lines, then it is quite easy. First you find out what is the head loss per drop, then see that at that point how many head drops are actually occurring. You may consider, I have considered here 2.4, you may consider whole numbers, like you may consider 3, you may consider 2, it does not matter, but that is all an approximate number. So, graphically you have to visualize that how many head drops are actually occurring at that point. So, the head drop, if the number of head drops at that. So, again coming back to the problem, so basically the head loss per drop you have to find out, and you have to graphically visualize that how many number of head drops are actually being observed. It may be a full number, it may be an integer, it may be a fractional, it does not matter. You can even consider it as 3 head drops here. So, the total head that you have considered should be subtracted from the head drop at that point in order to get the head at that point. And as we all know that basically the total head will be equivalent to the piezometric head, which in turn is equivalent to the pressure head plus the datum head. So, you find out the total head multiplied with gamma W, and then you will find out the pressure at that point. Now, this helps in sometimes find out the effective stress at that point, because you know that once you find out the total stress, then subtract this pore water pressure from that number, then you will get the effective stress at that point. And in order to get the pore water pressure actually, then you have to first know the phreatic line, because without graphical interpretation you cannot find out what is the pore water pressure at that point. So, in order to find out the graphical interpretation, you have to take help of the basic mathematical equation of all the parabolas of the parabola, and you have to find out some basic relations like distance of the directrix from the focus, or the distance of the vertex from the focus of the parabola, and like the distance of the vertex from the focus of the parabola is half the distance of the directrix from the focus of the parabola, or the basic relations that I have covered here, like this y0 by 2 and d square plus h square minus d and all these things. And anisotropic flow nets, as we all know, that it should be multiplied with a factor that basically modifies the horizontal distance while keeps the vertical distances same, and drawing the flow net and then finding out what is the seepage loss. So, this ends the permeability chapter. Now we are going to discuss about the consolidation problems. Now before we start about the consolidation problem, today actually we are going to discuss a very simple problem on consolidation, and that requires some basic concepts of over consolidation. So let us start with the problem. And area under consideration is known to have been a lake at the beginning of Quaternary era. Lake bottom consisted of a sand layer 55.70 meter thick, overlaying a clay layer of 7.6 meter thickness. Now let us see the diagram, how does it look like. So this is how it looks like. And this is where the present water table is, and a building is constructed here. So this is, let us say, the lake bottom. Now how the lake bottom, now this is where the building is constructed, and this view when enlarged of the lake bottom looks somewhat like this. This is the lake, this is the layer of sand, this is the layer of clay, because this is a sand layer of 55.70 meter. So this is layer is a 55.70 meter, and this is a clay layer of 7.6 meter thick, and this is the lake. So with time the lake disappeared, and the lake bottom became a plateau through which a river carved a deep valley. So this is how the figure now looks like. This is the river, this is the plateau, and it is being carved through a deep valley. Now the plateau is now some 45 meter above the bottom of this valley. So this plateau, this height is somewhat 45 meter, okay, it is said, and the water in the river is 1.5 meter below the level of the valley. So water in river is 1.5 meter below level of valley. So that means this is the water level, this I have said as this is the water level. So this height is some 1.5 meter. Now it is difficult to draw here, but this height is somewhat 1.5 meter. That means if you enlarge this part, let us say, so this is how it looks like. This, then the river carved a deep valley, then here this is the river, this is the water table, this is the phreatic line, and this height is 1.5 meter. This is the plateau part. Okay. So, this goes up, this from this is here. So, from this point it is 45 meter, 45 meter, and this is where the building is constructed. Now, the first question that is asked is, given the sand layer has gamma B as 1.04 gamma W, gamma S as 1.76 gamma W, clay layer has W as 35%, WL, that means the liquid limit, as 45%, and GS, or the specific gravity of soil solids, as 2.78. You are asked to find out the pre-consolidation pressure first. Now, how do you calculate the pre-consolidation pressure? Because finding out the pre-consolidation pressure is the first fact that requires nothing. Now, you know that basically a pre-consolidation pressure is basically the pressure at which the soil has been subjected to the maximum stress or the largest effective vertical stress in its geological history. So, basically you have to consider from the time where the lake existed to the point when basically the lake has disappeared. Now, the lake disappeared means basically what happened is that the pressure got released. So, basically you have to find out the pre-consolidation pressure at that time when basically the lake existed. So, at the time when the lake existed, if you consider, then the sigma dash, okay, because you have to find out the pre-consolidation pressure, where the pre-consolidation pressure at the, without neglecting the effect of clay. So, sigma dash will be equal to how much for the sand layer. So, sigma dash will be equal to how much at that point. At that point, if you consider the lake exists at the top, then this entire length of sand was 55.70 meter, and we have to neglect the weight of clay. That means, you have to neglect the 7.6 meter height. So, 55.70 multiplied by 1.04 gamma W. So, that means 55.70 into 10.4, because the unit weight of water is 10. So, this comes out to be 579 kPa. So, this is the time when the lake existed at that time. Now, when the lake has got off, then basically the overburden pressure was released. So, obviously, this is the largest stress that was experienced in the history. So, that is why this is the pre-consolidation pressure. In the second question, it is asked that, as I was telling from the beginning, that a building was constructed on the other side. So, basically if that lake was removed and if it was made a settlement, then in almost in all the cases in practical field problems, you have to find out that what is the settlement. So, you have to first find out that what is the stress that is imparted by the building, which is given here. It is given as 0.9 ton per centimeter square. So, this is delta sigma, that is the stress, that is the extra stress that is permitted in this layer. So, in order to find out that, let us see that how we would proceed. Now, first let us find out that the settlement, first let us analyze the situation. See, for sand there will be only elastic settlement, for sand there will be no consolidation settlement. Sandstone settlement is only possible for clay. So, the only possible settlement is due to the layer of that 7.6, is due to this clay layer of 7.6 meter. So, in that case, we have to first find out that what is the vertical effective stress at the mid height of the clay, that is the basic thing. So, for that what we will do is that we have to first find out the gamma B of clay or the unit weight of clay. Now, how to find out the unit weight of clay? Now, we all know that gamma B is equal to gamma S into 1 plus W by 1 plus E, or basically you can go from simply GS plus AC by 1 plus E into gamma W. Okay, either of this formula. Now, if you consider this, then basically we have to find out E. Now, E also we know how, WG is equal to AC from the basic soil relations. Now, if we consider S equal to 1 or saturation 100%, now that we have to consider anyways, because it is the bottom of the lake. So, basically it is always saturated. So, E is equal to W into G. Now, G is given as 2.78 and W is given as 0.35. So, multiply both of them, we will get 0.973. W is given as 35%, D is given as 2.78. So, we get E equal to 0.973. So, moving to gamma B, GS plus SE by 1 plus E into gamma W. So, this comes out to be GS plus E by 1 plus E into gamma W. Okay. Now, GS is given as again how much? 2.78. 2.78 plus E you found out to be 0.973 divided by 1 plus 0.973 into gamma W. So, this comes out to be as 19 kN per meter cube, taking gamma W as 10 kN per meter cube. Considering the saturated, now because this is equivalent to gamma S, because S is equal to 100% for this entire layer. Now, there is one more thing that you have to consider in this case. Remember that basically the water table, wherever the water table is, it is below the, it is at the clay layer, and basically there will be a capillary rise in the sand layer. So, in the capillary zone, we will consider the sand to be completely saturated. If that is the case, then for dry sand the gamma B, for dry sand the gamma B is given as 10.4, means 10.4 kilonewton per meter cube. Then gamma S saturated, it is already said that what is the saturated sand gamma weight, and that is given that the weight density of the water table, this is the weight density of the water table. So, it is given as 1.76 times of gamma W. Now, this weight density, so this is equivalent to 17.6 kilonewton per meter cube. Okay. So, then the thickness, now you have to find out that what is the height of this capillary zone, what is the height, or what is the height of this capillary zone. So, height of this capillary zone, let us consider that this height of this capillary zone to be 1.5 meter. Now, you can find this out easily from H by C into D10 from this Hazen's formula, okay, but it is given that the saturated sand, but here in this problem it is given that the height of the capillary zone is 1.5 meter. So, since the height of the capillary zone is 1.5 meter, so we will have sigma dot, that means that the middle of the clay layer, if you consider, now the sand layer has a height of capillary zone of 1.5 meter, then 7.6 meter, you have to find the height at here, there is a mid height, what is the sigma naught, and above it this length is 55.70 minus 1.5 meter. So, if you find it out, then this is 1.50 into, now what is the unit weight of sand at that point is 17.6. So, 17.6 kilonewton per meter cube, meter square. This is for this layer. For half of the clay it will be 7.6 by 2 plus 19 minus 10 kilonewton per meter square. Now, there is a reason why I added 17.6 here. The reason why I did it is basically because of this fact that 1.50 into, if you consider the dry weight of sand, then it will be 7.6 kilonewton per meter cube, but since it is in capillary zone, so you have to add the water unit weight instead of subtracting it, while in the case of clay, since it is below the water table, so basically you have to subtract the unit weight. So, that is known to everybody because this has already been taught in the effective stress of capillaries, effective stress in capillary rise. And the last and the final part is basically for the topmost part 55.70 minus, now you are considering this at the time when basically the building is drawn. So, basically this has been carved off, and now only if you can see only 45 plus 1.5, that means if this is the height of the layer initially, that means if initially it was 15.70 meter at the beginning, now only the layer of sand that remains is 45 plus 1.5. So, obviously this will be 45 plus 1.5 into 7.6 Newton per meter square, because you have to find out the effective stress at that point. So the total comes out to be somewhere near about 160.5 kPa or kilonewton per meter square. Now again let me discuss, because a little of effective stress has come in this concept. So let me again discuss that in that how did I did this. This has been considered at the point where basically the building is constructed. So when the point where the building is constructed, I have already said that the river has sculpted a deep valley. That means that layer of sand has actually vanished. So now only 1.5 meter of this sand, only 1.5 meter remains, and out of this only 45 meter at the top there is a plateau. So 1.5 meter is basically the height of the capillary zone. That is why I said that the question where basically the capillary zone is already said to be given in the question, that is 1.5 meter. If it is not given, you can find out from this Hazen's capillary constant H by C into D10, where basically the Hazen's constant has to be given. So since 1.5 meter is already given, so we already said that the saturated sand has a unit weight of, I have already said that the weight of the saturated sand is 1.76 gamma W. So obviously 1.76, so basically the weight of the sand in the capillary zone will be 1.50 into 7.6 due to sand only. But as you know from the concept of effective stress, that basically 10 kilonewton per meter square has to be added. So 1.50 into 10, because the suction, because it is experiencing suction, because it is experiencing capillary rise, so that is why it is multiplied with 10 in order to increase the effective stress. So 1.50 into 7.6 plus 1.50 into 10 kilonewton per meter square is the final value for this part. Now since the river has carved a deep valley, so basically 45 plus 1.5 is the total height that has been removed due to the lake. So 45 plus 1.5 has been totally removed. So 45 plus 1.5, that is why subtracted from the original length of 55.570 sand layer, and again it is multiplied with 7.6 because it is just the dry unit weight. So finally that all came out to be 160.5 kPa. Now once you know that 160.5 kPa, you also know that the value of delta sigma is 0.9 ton per centimeter square. Okay. Now actually the unit of 1 DAN per centimeter square is equivalent to 100 kPa. So this is basically equivalent to 90 kPa. Let us convert everything into kPa. So once this is done, now it is easy to calculate the settlement, because you already know that delta sigma is 90 kPa, the stress at the middle of the clay layer. I hope that this 7.6 by 2, so 3.8, so stress at the middle of the clay layer you know how to be 160.5 kPa. So from there you can find out that what is the settlement, because you know that the settlement formula is Cc by 1 plus E naught. E naught we have already found it out for the clay layer, that is also known to us, because the E naught is 0.973 into H into log 10 of sigma naught plus del sigma by sigma naught. But there is one more trick here, because the clay layer initially we said, even though we said that we ignored the weight of clay, but the clay layer was actually said to be over consolidated, because now the overburden pressure from the top of the clay layer has been removed. So obviously this settlement has to be added with another settlement that basically is due to the over consolidated clay layer. Right now I am stopping it here, because so right now I am stopping it here, and in the next lecture we will consider the effect of the more on problems on consolidation and how you have to take the effect of pre-consolidation settlement in order to find out the answer of this problem. Thank you.